Hello everyone, myself Dr. Ranjith Kumar Gatla, working as an associate professor in the Department of Electrical and Electronics Engineering at Institute of Aeronautical Engineering. So in today's class, we are going to discuss the topic is about capacitors and the capacitance. So which means in this today's class, we are going to discuss what is the concept of capacitor and what are the uses of the capacitor and how we can calculate the capacitance. And the capacitance will depends on what are the parameters that can affect the capacitance of a capacitor. So these are the things that we are going to discuss in today's class. So to understand first what is the capacitance. So first let us understand what is the electrostatic field, right? So there are two different fields. One is electromagnetic field, another one is the electrostatic field. So in this case, now we are trying to understand what is electrostatic field, because as we know the general function of the capacitor, okay, so it stores the energy in the form of electrostatic, okay. So which means not only actually here it will store, okay, it is also oppose the sudden change in voltages. The purpose of the capacitor is it will oppose the sudden change in the capacitor, sudden change in the voltage. So that is also one of the function of the capacitor, okay. So here, to better understand here, I have considered the two plates, namely call it as A and B. So here the plate A having the positive charge and the plate B having the negative charge, right? So suppose if an electron, of course we know that electron having the negative charge. So if you place an electron in between these plates, then the force will act on the electron tending to push it away from the negative plate, right? So negative plate B and towards the positive plate A, which means here there are two plates, which are placed and with a distance of, let us consider D, and the distance between these two plates is D. And here the plate A is having the positive charge and plate B having the negative charge. So suppose if you placed an electron which is having the negative charge in between the plates A and B, then it will, some force will be act on that particular electron, okay, so that here, because as we know, the same charges will repel and opposite charges will attract each other. So which means here we are placed the negative charge. So this electron will repel with this positive charge B, okay, and attracts towards the positive charge, or push away from the negative charge B, okay, and attracts towards the positive charge A. Similarly, if you place a positive charge in between these two plates, then the opposite way it will act, which means here the plate A will repel or a tendency to push it away from the plate A, and here the plate B, because it is having the negative charge, so it will try to get attracts towards the plate B, right? So which means here an electric charge experiences a force, which means here the force either maybe it is opposing force or maybe the attracting force. So which means here the positive or the negative charge, whatever the charge it may be, okay. So which means here the electric charge experiences a force. If you place that particular charge in between these two plates, then that field is called that force is called the electrostatic field. That force is called the electrostatic field. Of course, here the force and the particular field also having the direction, which means here suppose if you placed a positive charge, then the force will be towards the negative plate B, which means here the force is from A to B. So which is like this. So here you will be having the direction of the force also, right? So the electrostatic field is nothing but an electric charge experiences a force is called as an electrostatic field. So when it will experiences a force, either it may be positive or negative charge. If you placed in between the two plates, okay, so then it will attract or repel, okay, based on the type of charge that you have placed in between these two plates, right? So that is meant by the electrostatic field. Then Here, there are different types of forces that will be act. Okay, I mean that is depends on, because in the previous case that we have considered the two plates having the different polarities, okay, are placed with a certain distance d. So that is the one case. Suppose here, as you can see here, this is isolated point charge. Okay, so only one point charge is there. Okay, so based on the surrounding field, either it will be attract or repel, okay, with the other the charges. Okay, either it may be, if it is a other positive charge, then it will move away from that particular positive charge, and if it is a negative charge, then it will try to move towards that particular negative charge. Then here, suppose here the adjacent charges, okay, of opposite polarities. Then if there is a adjacent charge of opposite polarities, okay, which means here this is isolated charge, means here it is trying to, okay, trying to look for the other charges. Okay, so surrounding the particular charge, whether is there any positive or negative charge. Okay, so if there is a positive charge, then it will try to repel with that positive charge, and if there is a negative charge, then it will try to move towards that negative charge because of this force in between those two charges. Similarly, if you place just adjacent charges with opposite polarities, so one is positive, another one is negative, then here the force here, as you can see here, so the force is moving, okay, from positive to negative, right? So, because high polarity to low polarity, some positive to negative. And of course here, what are the parameters that will affect this force, okay, or the electrostatic field or that particular force. So here the force can be affected by here the charges q1, q2, and the distance between those two the charges, right? So let us consider here the charge of this particular positive charge is q1, okay, and here it is, let us consider q2. Then here the force between these two charges is proportional to the product of the individual charges, that is q1 into q2, right, and is inversely proportional to the distance, because of course here when we increase the distance, then the attractive or repulsion force between these two charges will definitely decrease, right? If you place very near, then the force between these two charges will be very high. So that's why here the force which is inversely proportional to the square root of the distance between these two charges. Or in other words, you can write this one, the force is equal to k into q1 q2 by d2. Okay, but here we usually k is a constant, and the value of the k here it is 9 into 10 to the power of 9. So this is the force equation. Then coming to the capacitance, what is capacitance, right? So let the charge be positive coulombs on one plate, same like the previous case that we have considered, okay, and the negative coulombs on the other. Then the polarities of this pair of the plates which determine how much charge corresponding to the given potential difference between the plates is called as the capacitance. So the capacitance is nothing but, so let us consider a two plates, okay. So on one plate, let us consider here it is the positive coulombs charge or positive q coulombs charge, and on the another plate, if you are having the negative q coulombs on the other, then the property of this pair of plates which determine how much charge corresponding to the given potential difference between these two plates is called as a capacitance. So in other words, that's why here the capacitance C is defined as Q by V. So here Q is the charge and V is the potential difference between those two plates, right? So that is how here another function of the capacitor is it will oppose the sudden change in the voltage, right? So this is the basic definition about the capacitance. So which means here from this equation, again one more thing also we can understand here, the capacitance C is directly proportional to the charge of that particular either maybe the positive or the negative plate, okay, the charge, and here it is inversely proportional to the potential difference between the two plates. Then of course here how it look like the capacitor, that we know already, the basic the construction of the capacitor, okay, the internal structure of the capacitor. So here, as we know, the capacitor consisting of the two plates, and the two plates are separated by an insulating material, right? So that insulating material we usually known it as a dielectric material. right? So, which means that's what, as I told you here, the capacitor has an ability to store the quantity of static electricity, or it will store the energy in the form of static electricity. Okay, or a static electricity, right? So that is what another function of the capacitor, right? Of course, generally, at the basic level, okay, the function of the resistor is it opposes the flow of charge, right? And when coming to the capacitor and the inductor, it will store the energy. Okay, so one it can store in the form of electrical, okay, another it can store in the form of the magnetic field, right? So the capacitor it stores the energy in the form of electric field, right? And the inductor it will store the energy in the form of magnetic field. That is the only difference between the capacitor and inductor. So that's why here, before going to discuss about what is capacitor and capacitance, we started with the electrostatic field. Okay, so in the inductor we start with electromagnetic field, because here the capacitor stores the energy in the form of electric field. Okay, so that's why first we discussed what is electrostatic field. Okay, so which is nothing but a force, right? Then here, of course, there are two different types of capacitors. Okay, for our differentiation, one is fixed capacitor, another one is the variable capacitor. So which means here, this is the symbol of the capacitor that we know. Okay, and the unit of the capacitor is also farad. Okay, but in simply we represent with the capital F. So here, this is the fixed capacitor is nothing but, suppose if you take a capacitor, so suppose if that value of the capacitor here it is, let us consider 10 microfarads, then this capacitance value is constant, okay, for that particular capacitor. So for that particular capacitor, the capacitor value is always the 10 microfarads. And when coming to the variable capacitor, so the variable capacitor, which means the range here it is, let us consider here some 10 to 20 microfarads. So which means this capacitor, the capacitance of this capacitor can be, okay, variable from 10 to 20 microfarads, right? So that we can change. I mean, of course, there is some knob kind of things are there. So by varying that by adjusting the particular knob, okay, or by using the particular knob, so we can adjust the value of this capacitor, the capacitance of this capacitor in between 20 and 10 and 20 microfarads. Okay, just for understanding purpose, I have mentioned. Of course, there are various range of variable capacitors also there. So for our differentiation, the symbol. So here, this is for the symbol of the variable capacitor. Okay, this is for the symbol of the fixed capacitor. Then here the charge I is equal to I into T coulomb. So here I is equal to the current and T is the time. So how much the current flowing through that particular conductor. So that is mean by this particular charge. Okay, so that's what as I mentioned. So where I is the current in amperes and T is the time in seconds. Okay, so here just to try to remember these equations, okay, which means these equations relate the various parameters related to the capacitors, because in the next we are trying to solve some numerical problems based on these concepts. Yeah, so here then based on the concepts that we have discussed, what is the capacitor and the capacitance, now we are going to discuss some numerical problems, right? So first let me read about the first problem. The first problem here it is, determine the potential difference across a 4 microfarad capacitor when charged with 5 coulombs, okay, 5 millicoulombs, and find the charge on a 50 picofarad capacitor when the voltage applied to it is 2 kilovolts, right? So here, first of all, they ask us to determine the potential difference across the 4 microfarads capacitor, which means here they given that C is equal to 4 microfarads, and when charged with, okay, so here which means Q, the charge is equal to 5 millicoulombs, right? And first of all, what we have to find the charge on a 50 picofarad capacitor when, okay, yeah, this is the second bit. Okay, the first bit is first let us try to solve the first one. Okay, so the potential difference, so already we know the C is equal to Q by V. Okay, so here Q is the charge and V is the potential difference across the two capacitor plates. Okay, so then see, So from this here, C we know and Q know. So V is equal to Q by C, right? So Q is here 5 millicoulombs. So that's why 5 into 10 to the power of minus 3. And C here it is 4 microfarads. So micro means 10 to the power of minus 6. So 4 into 10 to the power of minus 6. If we substitute, then here by simplifying this, then you will get the value. Here it is the potential difference across these two, across the plates of a capacitor having the capacitance of 4 microfarads. Here it is 1.25 kilovolts. Then in the second case, they have given the charge Q. Okay, what is that? The capacitance C, which is 50 picofarads. Okay, 50 picofarads. Pico is nothing but 10 to the power of minus 12. Okay, so that's why here it is 50 into 10 to the power of minus 12 farads. And the voltage, the potential or the voltage applied here it is 2 kilowatts. Okay, 2 kilovolts. So which means 2 into 10 to the power of 3. Then as we know again from the basic fundamental equation. Okay, so here what they are asked us to find Q. So which means here C is equal to Q by V. This is the standard equation. So from that what we need to find Q is equal to C into V. Just substitute the value of C and V here. Then you will get the value here. Hence the charge here it is 0.1 into 10 to the power of minus 6, which means here we know the charge for the units for the charge here it is coulombs. So here it is microcoulombs, 0.01, because here 10 to the power of minus 6 can be replaced with the micro. So hence the charge is equal to 0.1 microcoulombs, right? Then the second question. In the second question, first a direct current of 4 amperes flows into a previously uncharged 20 microfarad capacitor for 3 milliseconds. Then determine the potential difference between the plates, right? So actually they ask us to find the potential difference. Okay, so because the equation they're related to the potential difference, that we know only this one. Okay, so which means V is equal to Q by C. But we know only C, but we don't know the value of the Q directly. Okay, but we know previously we have discussed the charge Q is equal to I into T, right? So we know the value of I is equal to here that they have given 4 amperes and T is equal to here that is 3 milliseconds, right? So just substitute these two values, then you will get the value of the Q. Okay, so here the Q value here it is 4 into 3. Okay, so 12 into 10 to the power of minus 3, which means here which is 12 millicoulombs. Then substitute this 12 millicoulombs in this Q in the here the Q. Okay, then C we know already the capacitor is 20 microfarads, so which means 20 into 10 to the power of minus 6. Then by substituting this, all you will get here it is 600 watts. Hence the potential difference. Okay, so the potential difference between the two plates here it is 600 volts. So this is how we need to find the we need to solve the problem based on the concepts which we have discussed previously, right? Then, okay, the next concept here it is the electric flux density, because before third, I think in the fourth module we discussed about the magnetic flux, but here the electric flux density is also there, which is related to the capacitor. So here the electric flux density we usually represented it as the capital D. So which is defined as the amount of flux passing through a defined area A. Okay, so that is perpendicular to the direction of the flux. Okay, so that is what the electric flux density. And in R simply the electric flux density here we can represent it as a D is equal to Q by A, and the units are, because here the Q units is coulombs and A units is meter square, so coulombs per meter square, right? Okay, so sometimes the electric flux density is also called as the charge density. Okay, sometimes we usually represented it as this rho symbol also. Okay, so then based on that we are going to solve some more problems. So let us read the third problem. Two parallel rectangular plates measuring 20 centimeters by 40 centimeters carry an electric charge. Okay, which means the rectangular plate measurements are 20 by 40. Okay, an electric charge of 0.2 microcoulombs, and calculate the electric flux density. Okay, so that we know charge by area, then we can directly get. and if the plates are spaced 5 mm apart and the voltage between them is 0.25 kilowatts, determine the electric field strength. That we know. Okay. So first of all, we need to find the electric flux density. So as we know, the electric flux density D is equal to Q by A. Just now we have discussed. So here Q is the charge and A is the area of that particular plate. So here, of course, they have given the data Q is equal to 0.2 microcoulombs. So which means 0.2 into 10 to the power of minus 6 coulombs. And the area here it is 20 cross 40, which means L into B. So 20 into 40, you will get 800 into 10 to the power of minus 4 meter square, right? So because they have given in the centimeters, so this we have converted into the meters. Then substitute in the electric flux density equation Q by A. So substitute the value of Q and A. Then after substituting, you just simplify. Then you will get finally the flux density here it is equal to 2.5 microcoulombs per meter square, because the units for the flux density is coulombs per meter square. So here we got the value 2.5 microcoulombs per meter square. That is the flux density. Then after that, what they are asking us to find, determine the electric field strength. Okay, so that is E is equal to V by D. So that also we have discussed. Here V is the potential difference between the plates and D is the distance between the two plates. Of course, they have given the potential difference here. It is equal to 0.25 kilovolts and the distance is also 5 mm. Okay, so you just convert this 0.25 into the volts. Okay, so which means here 250 volts, and here the 5 mm into the meter, so 5 into 10 to the power of minus 3 meters. So that the electric field strength E is equal to 50 kilovolts per meter, because here the unit for this particular electric strength is equal to volt per meter, because here V by D, because we measured in terms of volts and D we measured in terms of meters. Then the parallel plate capacitor. Okay, so if you are having a two parallel plates, okay, and then the distance between the two parallel plates here it is, let us consider D. Okay, and that of course, as we know, the basic structure of the capacitor, it is having the two plates, okay, with opposite polarities, and in between them are the two plates are separated with a dielectric material. So let us consider here the relative permittivity of that particular dielectric material. Here it is sigma R. Okay, so then the capacitance of that particular capacitor is depends on the terms sigma naught sigma R into A by D. So here A is area of the plates, of course, because the two plates having should be having the same area, and D is the distance between the plates, and here sigma naught and sigma R, okay, are the are sometimes here epsilon naught and epsilon R also sometimes they call it as. Okay, so here are epsilon naught, here it is the constant value, and the value of this epsilon naught here it is equal to 8.85 into 10 to the power of minus 12 farads per meter. Then here epsilon R is equal to relative permittivity. Okay, and A is area of one plate in meter square, and D is the thickness of a dielectric material in meters. Which means the thickness R we can also call it as the distance between the two plates also, because here the two plates are separated with the dielectric material, right? Or the thickness of the dielectric material is equal to the distance between the two plates, right? So that's why here we can make it as the thickness or the distance between the two plates. Okay, so based on this particular concept also, now we are going to discuss one more problem. So here a ceramic capacitor has an effective plate area of 4 centimeter square separated by 0.1 mm of ceramic of relative permittivity 100, and calculate the capacitance of the capacitor in picofarads. And second bit here it is, if the capacitor in part A is given a charge of 1.2 microcoulombs, and what will be the potential difference between the plates? So which means first of all we have to calculate the capacitance of the capacitor. Okay, so first of all we have to calculate the capacitance of the capacitor C. Just now we have discussed the equation for the C, which is equal to epsilon naught into epsilon R into A by D. So here epsilon naught value, this is constant. Okay, so we know, and epsilon R that they have given, which is 100, and A, okay, A also 4 centimeter square, just we need to convert into the meter square, and then the distance here it is 0.1 mm. Of course we need to convert again into the meters. Then substitute all these values in this particular equation and simplify, then you will get the answer for that capacitance of that particular capacitor. Here it is 3540 picofarads. Then now if the capacitor in the part A is given, okay, which means for this capacitor C, and then the charge Q is equal to 1.2 microfarads, then what is the potential difference between the plates? Of course, again direct equation. Okay, so V is equal to Q by C, then substitute the value of Q, which is 1.2 into 10 to the power of minus 6 farads, and here C here, sorry, Q 1.2 microcoulombs, okay, which means 1.2 into 10 to the power of minus 6, and C here is equal to 3540 into 10 to the power of minus 12. Then if you simplify, then you will get the potential difference between these two plates here, it is 339 volts, right? So this is the potential difference between these two plates. The capacitors are connected in series and parallel, so that we know. Okay, which means if the two or more capacitors are connected in series, then what is the capacitance between, or the equivalent capacitance between those capacitors? And similarly, if the two or more capacitors are connected in parallel, then what is the equivalence capacitance between those two capacitors, right? Or those capacitors. So we know if the capacitors are connected in parallel, then the equivalent capacitance between those capacitors C is equal to C1 plus C2 plus C3. Just we need to add the capacitance of the individual capacitors. So the equivalent capacitance across the capacitors connected in parallel is equal to the sum of the capacitance of sum of the individual capacitance of the particular capacitors. Then similarly, if the capacitors are connected in series, then the equivalent capacitance here it is equal to the reciprocal of the individual capacitance, the sum of the reciprocal of the individual capacitance. So which means 1 by C is equal to 1 by C1 plus 1 by C2 plus 1 by C3. So this is about the capacitance, and then based on that we can discuss one problem. Of course, here there are two capacitors which are connected. Suppose if these two capacitors are connected in parallel, then what is the capacitance, and connected in series, what is the capacitance? So connected in parallel, then we need to add these two, so 6 plus 4, which is equal to 10 microfarads. And if those two are connected in parallel, okay, so which means here 1 by C is equal to 1 by C1 plus 1 by C2. So if you simplify, then you will get C is equal to C1 C2 by C1 plus C2. And if you substitute the C1 C2 values in this particular equation, then you will get the value of C is equal to 2.4 microfarads, right? So this is about the capacitor and the capacitance in because this is okay. So in the next class, we will discuss the next topic. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.